Greetings, we are from Group 5 and the project that we are assigned is the wheelchair level propulsion system. The design of this wheelchair is aimed as an alternative to the current models that exist in the market. The objective of this wheelchair is to ensure that it is convenient and user-friendly when it is in use. This will help in reducing the force needed to move the wheelchair. Some of the specifications that were considered when designing the wheelchair are that the maximum weight capacity that this wheelchair can hold is 150 kg. Besides that, the maximum length of the lever is 0.5 meters. This wheelchair should also be able to move forward and reverse.
So the operating condition is the known condition that we have before starting this calculation, which is the pushing force from the user. We consider the average, which is 130 Newton. The rotational speed of the wheel, which is 16 RPM. Rate this at the stop rotational speed for safety precaution. The speed ratio that we wanted is to 2:1, and the length of the lever, which is specified before, which is 0.5 meter only, and the maximum mass of a user is around 70 kilogram. And then we continue on to the net force input. For calculating the net force input, we need to consider a rolling resistance, which is equal to rolling resistance coefficient times the weight of the user. According to the table on the left side here, you can see is a list of rolling resistance coefficient according to the scenario. In this case, we consider as our C, which is 0.01. Then we put into the formula, and finally we get the net force input, which is around 129.3133 Newton. Next, we continue on the application coefficient. Since our system does not make use of a motor, we consider the application coefficient is considered as 1. And then the corrected power transmission, which is equal to power transmission times application coefficient. And since the application coefficient is 1, corrected power transmission is equal to the power transmission. And then we start searching for the number of small sprocket teeth necessary in order to achieve the speed ratio. We have omega s, which is the rotational speed of the small sprocket, which is equal to 16 revolution per minute, which is equal to 100 rad per minute. Why rad per minute? This is for the table that we are going to use in the next slide. And then we start searching for the power. Power is equal to torque times omega large sprocket, which omega is angular velocity of large sprocket. So power is equal to net force input times the length of the lever times the angular velocity of the large sprocket in watt. Alright, but in the end we convert it into kilowatt, which is power is equal to 0.05 kilowatt. Why kilowatt? We are going to be using this table, which involve a radian per minute and kilowatt. You can see here. So in our system, we'll be using only one line with 100 radian per minute. So basically, in this vertical line here, we are going to search for 0.05, which is almost really close to 0. And then we're going to extend it until here. And then here we refer to the diagonal line. The diagonal line will decide how much teeth necessary for our small sprocket and the type of chain. Here we can see, since it is around here, right? It is around 23 teeth. With the chain necessary is CHE25. You can look up the specification of the chain with Google. So for the number of large sprocket teeth and 1, which is quite simple, is number of small sprocket teeth times the speed ratio that we wanted, is equal to 46 teeth. And the shaft diameter, since we are going to custom make the shaft diameter, it can fit any size of the hole in the sprocket. The distance between the center, the distance is decided to be 0.3 meter. So when one of our member physically measured the distance necessary, so that the height of the lever is equal to the user's hand. We consider this as a chair. Basically, we want the level to be around this height, which is equal to the user's hand. And basically, the length of the small sprocket and the large sprocket, small will be here, large will be here, is around 0.3 meter. And lastly, we will be calculating the number of link for the chain. So the formula for the number of link is length for chain, which is represented by LP, which is actually means L over P, is equal to this one. So basically, all we need to do is input the N1, N2, the C, and the P, the pitch length of the chain, where we just Google it before based on the CHE25, and lastly we get 129.2718, and then we round it up into 130, which is according to the source, it is recommended to be the number of the link to be 100 in even numbers, so we hit perfectly the even numbers with rounding up.
Our design consists of 7 parts. Part 1 is the chain inner link. Based on our calculations, we have decided to choose CHE25 for its parameters. For our second part, which is the chain of the link, we also decided to choose the same part number, which is CHE25 for its parameters, since they will be linked together. Large shaft will be the third part, and it is designed to fit the large sprocket and lever together. Small shaft is the fourth part, which is designed to fit the small sprocket. The small sprocket is the fifth part. The outer diameter and the pitch diameter is chosen so that it will fit in the chain and at the same time will have 23 teeth. The sixth part will be the large sprocket. The outer diameter and the pitch diameter is chosen so that it will have 46 teeth and will also fit the chain. And as you can see, there is another teeth in the middle. It is to transfer motion from the lever to the sprocket. And our last part is the lever. The lever length is chosen based on the maximum length given, which is 0.5 meter including the handle. And as you can see, the lever also consists of teeth, which is used to translate the motion from the lever to the sprocket. So after we assemble all the parts, our lever propulsion mechanism will look like this. Moving to material selection. For the wheel rim, we decided to choose alloy steel. Why? Because it has high tensile strength, hence able to withstand excessive force. It is ductile and it has corrosion resistance. Next is the wheel frame. We decided to choose aluminum. Aluminum is a non-ferrous metal, thus having high corrosion resistance. It is also lightweight, thus can be easily moved around without requiring much force. For the sprocket, we decided to choose medium carbon steel. Why? Because it has excellent wear resistance, thus increasing the lifespan. It is strong and durable, and also cost effective. For the chain, we decided to choose steel. Steel is strong and durable, excellent wear resistance, thus increasing lifespan, and it has corrosion resistance. And for the lever, we choose medium carbon steel. Why? Because it has corrosion resistance and is also has excellent wear resistance, which will increase the lifespan.
For selection process, we begin with the frame building. It involves in the machining of the wheelchair frame parts and components into precise measurement. For example, sheet aluminum parts for the handle assemblies are cut and shaped in a special purpose booth, after which cut and bend components are transferred to a location within a workshop complex for assembling into sub-units. Next is to produce wheelchair components. Producing various wheelchair components using the highly versatile and capable CNC milling machines. These will be run by highly competent and skilled personnel in order to ensure the quality of the craftsmanship. After that, assembling the main module, fitting all wheelchair parts such as seat, handles, harnesses, and brake units, and results in a complete product ready for testing. Speaking of testing, the next one is WHO standards testing. Going through necessary checks in line with safety standards, which involve alignment, terrain test, and impact test. The next one is packing. It is individually packed along with separate ancillary items such as padded cushion, rug and toy, and all of that are added to the wheelchair package ready for distribution. And finally, it will undergo testing according to international standard ISO 7176, which allow it to undergo various testing including stringent stability, fatigue and durability testing to simulate the rough terrain which might be experienced in developing countries, which was done by University of Western Australia Engineering Department.
Now we'll be looking at the failure mode and effect analysis table. There are 4 types of failure modes that may occur, which is yielding, misalignment, welding failure, as well as wear and tear. For the wheel rim component, the possible cause of failure is that the spokes on the rim undergoes high tension, which will cause the risk priority number to be 60. Next, the chain may undergo unbalance in sprockets, which will give the RPM value to be 72. Next, the wheelchair component might undergo overloading or improper use, which will create an RPM value of 70. Next, for the brakes, the brake pads are worn due to contact with wheels, which will give RPM of 60. So based on the RPM value, we can conclude that the components of D, A and C will be at medium risk, whereas the chain, which is component B, will be in high risk zone.
At the left shows a wheelchair with a dual chain system on both sides. In order for the wheelchair to move forward, the user must slide the lever and lock in the outer chain system to move front end. In order to reverse, the user has to slide the lever and lock in the inner chain system to move backwards. Comparing with the model in the right hand side, where we can see that it shows a manual basic wheelchair which need more force applied to move. In order to move forward, user must hold the hand rim attached to the rear wheel and push forward. To move backwards, user have to hold the hand rim attached to the rear wheel and pull backwards. This costs more energy to be used by user to move a certain distance compared to the model that was designed at the left. The push and pull force on the lever are strong enough for the user to move around with ease. The use of a larger driver's sprocket will ensure that the user does not need to move the lever much to move the wheels. Thank you so much.